wasn't paying attention. I was looking at this.
Alright, so actually, so this proves it since, actually, so this shows that big F is a complex differential. I just showed that its derivative exists, and is this one. Its derivative exists, and is this one. And if this derivative exists by original definition, then F, big F, is holomorphic. And since little f is its derivative, little f is also holomorphic. But for that, we're going to have to actually prove 5 first to see that, in fact, holomorphic functions are infinitely differentiable. So it's like so Morera's theorem will be proved as soon as we show that the derivative of any holomorphic function is a holomorphic function. And then Morera's theorem is proved. So we still got to show that. But that's the only thing pending. What's next? And we're actually close to the Cauchy integral formula. So actually, yeah, no, right now. Do the Cauchy integral formula. And this will help us prove that a holomorphic function is infinitely differentiable. So now, remember the definition was that for every z0, so let's pick so we have the domain U, and we're going to pick a point P in U, the center. We're going to pick a point U such, P in U such that the disk around P of radius R is compactly contained in U, meaning that the closure of it is contained in U. So in other words, so here's U, here's P. We can find some R such that this disk is completely inside of U. If we can do that, if there exists such R, then a bunch of nice stuff follows. Such as this. For example, now pick a Z in this disk. So here's Z. Z could be P as well. It's any point inside the disk. And so not on the boundary of the disk. The boundary of it, I'd have to do that. Inside the disk, completely inside the disk. For this Z in there, actually, no, call it A. For any A inside here, we have this. We have that this function, we're going to define f sub A of Z to be, and this I'm using the notation from Bach-Newman. F sub A of Z, we're going to pick it to be f of Z minus f of A over Z minus A. And if Z is in the disk minus the disk of around P of R minus A. And it's going to be F prime of A if Z equals A. So really, this quotient is defined and it's holomorphic everywhere except at A. Because at A I'm dividing by 0. So that we just put what this the limit of this quotient is equal to. It's this guy, right? By the definition of F being holomorphic, and F's hollow. So we just define this little function, and since you're unioning you're going to union the domains, it's going to be holomorphic on the entire open disk, dpr. So which implies that this little f sub a is holomorphic. This is a little symbol for it. Holomorphic on the disk centered at P radius R. If this sub f sub a is holomorphic on this disk, then what? Then by Cauchy's integral theorem, we have that the integral around any curve is 0. So that pick gamma to be the boundary of the disk. And so we have the integral, the closed integral around boundary of this disk of f sub a of z, dz, is actually, but around the points, so remember, so inside the disk, everywhere inside the disk, the function is defined like this. at the point A, the function is defined like this. But we're integrating along this thing. Actually, this function is, I'm sorry, this function is holomorphic on all of you, actually. Not just at this, on all of you. By just adding this little point. So this is f of z, f of a over z minus a. And by the Cauchy integral theorem, since this function is holomorphic on u, this is 0. But now what? If this is 0, so forget about the left-hand side here, we have this guy is equal to 0. So actually, the integral, or on the boundary, is this f of z over z minus a dz minus f of a over z minus a, in which we bring this to the other side, right? We bring this to the other side. And actually, this is an integral with respect to z. F of a is a constant, so we pull them out. And we have this relation. This follows directly from the fact that this f sub a is holomorphic, meaning its integral around this disk is 0, so we have this relation. So now we just have to calculate this integral here. So actually we're going to do it for any case. So we want to calculate the integral around the boundary of some disk of radius r of 1 over z minus a. And actually I'm going to calculate it for any k, where k is an integer. Dz. So remember the line integral. So we parametrize the curve. We're integrating along the boundary of a disk. So we have to parametrize the curve. Let gamma of t be, wait, this is the disk centered at P. Wait, no. We're gonna actually, if this is A, no. If this is A, we're gonna put a disk around A and integrate along that boundary. So this is gonna be a disk around A actually. So gamma of t is gonna be A plus the radius of the circle, r, little r, e to the I theta. Gamma prime of t is just I times r times e to the I theta, dt. So this is just the integral, and this is from 0 to 2 pi, right? T in here. So this is integral from 0 to 2 pi of, we have, so I'm letting z be gamma of t. So z is gamma of t, which is a plus r e to the I theta minus a, is the point, the k, 1, and then dz is gamma prime of t dt is I r e to the I theta dt. Why am I using thetas and t's? Dt, no theta, t. And so what do I get here? I get, actually, so the I comes out, this I comes out, the R comes out, actually, well no, the R is, so I'm going to have, on the bottom here, the A's cancel, and I'll have R to the K, E to the I, T, it's not theta, it's T, I, T, K, and then here on the top, I have the I came out, I have a R, and I have I, E to the I, T, dt. So rewriting, this is just I over R to the K minus 1. Zero to 2 pi. E to the, what do I have? I have IT minus 1. So IT times 1 minus K actually. If I bring it to the top, it's 1 minus k. If I leave them on the bottom, because there's k of them on the bottom, it'll be k minus 1 on the bottom. It's negative of 8 dt. And now, this is a simple calculation. This is equal to, if k is 1, then this is, I'm integrating e to the 0 from 0 to 2 pi. E to the 0 is 0, right? So if k is 1, the answer is if k is 1, this is 1 minus 1, this is 1. This is r to the 0. So I have I times integral 1 from 2 pi, so it's 2 pi I, if k equals 1, right? You guys see that? I'll have, I'm integrating 1, so I'll have I over 1 times the integral of 1 dt from 0 to 2 pi. This is I times 2 pi minus 0. 2 pi I. If k is 1. And if k is not 1, if k is a different integer other than 1, this is 0. Because you'll integrate this and you'll get a 1 over, you'll get a 1 over k, 1 minus k here, down here on the bottom, times e to the it from 0 to 2 pi. But the whole thing is that, you'll get I to the e to the I 2 pi minus e to the I 0. When in this part of the integral, times whatever, times I over r to the 1 minus k. But this is 0. This is 1 minus 1. 1 minus 1, 0. So 0 if k is not 1. So that now, once we calculated this special integral, we go back to here. Because you're going to need this, I'm actually going to need this to show you guys later on expansion. And the rest of the theorem follows from this. So what? We just kept, so when k is 1, if I plug in k equals 1 here, that's what I have right there. So that k is 1, this is equal to f of a times 2 pi I. From which we get the Cauchy integral formula. Is that f of a, so remember, a is in some disk around P, radius r, contained in U. And the value at that a, f of a, is given by 1 over 2 pi I integral around the little disk around a of f of z over z minus a dz. And so what does this tell us? What does this mean? This tells us that holomorphic functions they're so continuous, basically, that the value at a is not even given by a itself. It's actually given by like the average of the values around a. That's like the cool part about them. So that I have some little ball and I have a point A. If I want to know what f of a is, I just integrate around that. Doesn't matter the radius of the circle. But that the value at a is not really given by the value at a. It's given by how the magnitude is given by how the function is around a, not necessarily at a. And this is arbitrary. A here was arbitrary. A is any guy in here. So that this holds for every a inside this disk. And that is the Cauchy integral formula. Now we're going to, real quick, now using this formula we can prove that every holomorphic function, we can prove 1 implies 5, that every holomorphic function has a power series expansion. And it's really simple. So now, so again, same setup. So pick A inside the disk around P, radius R inside U. That implies that the absolute value of P, A minus P, for example, So now I'm gonna change it to z. Let z be in here. So now I'm just gonna change it to z. If z is inside this disk, any point in there, that means that his distance from P is less than the radius of the circle, right? And let zeta be in the boundary of the disk. That implies that zeta minus P is actually equal to the radius of the circle, from which we get that z minus P over zeta minus P is less than 1, right? I'm saying this divided by this will be less than 1. Will be less than r over r, which is 1. And now I can use that to expand f of z. So f of z was, by the Cauchy integral formula, f of z was equal to 1 over 2 pi I integral around the boundary of some disk around point f of zeta minus z d zeta. So now we're going to expand it, but 1 over zeta minus z is actually 1 over zeta minus p plus p minus z is 1 over zeta minus p is 1 over 1 minus z minus p over zeta minus p. Right? And now, z minus p over zeta minus p, the absolute value of this is less than 1. You guys remember this formula? 1 over 1 minus x is x to the k. Right? Well, we're going to use it with this guy, z minus p, and this was convergent if the absolute value of x was less than 1. Well, the absolute value of this x is less than 1, our special x right here. So that we can expand it via this power series, and it's convergent. So this is 1 over zeta minus p, sum k equals 0 to infinity. What do I have? I have this to the k. So that's z minus p to the k over zeta minus p to the k. Bring this in, zeta minus p is right there, so plus 1. So that's what 1 over zeta minus z is equal to. So we go back to here and we have that f of z is 1 over 2 pi I integral around the boundary f of zeta over f of zeta times 1 over times this. Minus c 1 over 2 pi I. Sorry about my handwriting. What do I have? I have f of zeta times k equals 0 to infinity. Z minus p to the k over zeta minus p to the k plus 1 is zeta. And now, since we're assuming this is convergent, this is just line integrals convergent, we can exchange integration and summation signs. So this is sum k equals 0 to infinity of 1 over 2 pi I integral f of zeta over this guy. This depends on zeta. This z minus p here doesn't depend on zeta. This guy can pull out. This is zeta minus p to the k plus 1 d zeta freaking z minus p to the k. which we rewrite as sum k equals 0 to infinity c sub k z minus p to the k, where ck is 1 over 2 pi I integral boundary f theta over zeta minus z. Is it z or p? P. No, yeah, it's p. Where the coefficients are all, so the coefficients of our power series expansion are these coefficients. Hence, f of z is ck times, it's a power series centered at p, right? And from this, it's obvious that this thing is infinitely differentiable. It's a power series. You can differentiate as many times, and from this we get the generalized Cauchy integral formula, which we get formulas for the derivatives. So look, so this is f of z. If I do f prime of z, well, f prime of z is taking the derivative of this. What would it be? It would be k equals 0 to infinity k ck z minus p to the k minus 1. Right? The first term is 0. The first term is 0, so k equals 1. Ck z minus p to the k minus 1. And now do f prime, plug in p. Plug in the center of the thing. Into here. Everybody except the first term vanishes. You see that? Like, so I'll just get C1. Which was this guy, and so forth. And from this we get, so from this we can derive formulas for the derivatives of holomorphic functions at every p of any order. We have that f, like the kth derivative evaluated at p is actually k factorial times ck. It's k factorial times the coefficient. From where now we just divide by this. And we actually have that the coefficients of our power series expansion are actually f to the k at p over k factorial. If you guys remember Taylor series, this shows that holomorphic functions are real analytic. So you have, remember when I was talking about C1, C2, you have k times, so you have ck is k times continuously differentiable. You have C infinity means infinitely many times differentiable. You even have C omega. This means real analytic. A function is real analytic if it's equal to its power, to its Taylor series. Meaning, so right here, the ck is actually f to the k at p over k factorial times z minus p to the k. And this is exactly the Taylor series for f. This is the Taylor expansion at about p of f. So that this shows that every holomorphic function is also real analytic. The converse is not true though. Every real analytic function is not holomorphic. And bro, I don't know what else to do. Let's see. Okay. This is too much. Am I going too crazy? We need some feedback, guys. So I showed holomorphic functions are real analytic. Alright, so let's just finish off. What time is it? Looking like 5 already? Yeah, it's almost 5. So there's actually a lot of presentation still left, but we can finish off with a nice example, with a nice application of all this crap. You guys want to see it? Yeah! The application of this is the Cauchy integral formula. This was like originally the coolest part of my presentation. Obviously I didn't get to it like hours behind. mind already.
I only like that part.
Huh?
I only like that part.
Which part?
The part you just
The
read.
part that you gonna do.
Okay, so an application of the Cauchy integral formula. Suppose I want to integrate over the whole real line. Let f of x be 1 over x squared plus 1 squared. And suppose I want to calculate now the whole thing is this cool guy in here doesn't have a nice antiderivative over the real numbers. This doesn't have an antiderivative over the real numbers. Hence, you can't just do u substitution or blah 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 and calculate. But we could find what this guy is using the Cauchy integral formula. How do we do that? So this is what we want to compute. By the way, this guy just looks like this. When x equals 0, he's at 1 squared, he's at 1. And this guy's just like a little, he's kind of like a little bell curve. And we're talking, and this integral is the area under the curve, right? How much is that area? We want to know. So we complexify f, let f of z be 1 over z squared plus 1 squared. And the whole thing is the polynomial we bring over the complex numbers, the irreducible polynomials are linear, meaning we can factor the hell out of this. This is 1 over z squared plus 1 is z minus I, z plus I. Squared squares both of them. This is what's really nice about the complex numbers. And which we rewrite as, you'll see why right now, 1 over z plus I squared over z minus I squared. Equal to g of z over z minus I squared. So now we're going to integrate this guy along a really cool path here. It's going to be a semicircle, a half of a circle. So let this be a complex plane. Here's a point A. Here's negative A. Let gamma be the curve given by this. We're going to integrate along the real line from negative A to A, and then along the semicircle that connects them.
So you are saying that c squared plus 1 is equal to c, right?
Okay?
That one.
Z squared plus 1 is...
No, x squared plus 1 is equal to c, right?
X squared plus 1 is equal to z?
Yeah.
No.
C is equal to c squared. You got it?
Where?
Yeah, because x squared plus y squared is equal to c.
So r squared is the radius. No, so look, I'm trying to compute this integral. Just switch the x for a z and consider the function as a complex valued function. And factor this guy. The whole thing is over the real numbers he doesn't factor. Over the complex numbers,
So
z squared plus 1 is z minus
can be real and
z
can be
plus I.
c can be real and can be imaginary, right? Complex.
What?
C minus I, c plus 2.
Yeah,
Because it's c times c complement, right? Because
Z times z complement. I don't know what you're saying, bro.
because this c is c times c, right?
This z
Yeah.
is z times z? What? Yeah, look at what I'm doing. So I'm trying to evaluate this integral. So that I take the function of x that had this is a real valued function, and I just consider it the same function but as a complex variable. And over the complex numbers, so this function over the complex plane, it factors, because this z squared plus 1 is z plus I z minus I. This is z squared minus negative 1 squared. Well, minus negative 1 squared. It's z plus I z minus I. And we rewrite like this, and now we just use a Cauchy integral form. well, we define this constant, so gamma is this thing. We integrate along the real line, so here's I. We integrate along the real line and from negative a to a, and then just do a semicircle around there. And so call that thing gamma, and we have, so then what? So we decompose it, so the integral along gamma of f of z dz, we're going to decompose it as the integral from negative a to a f of z dz plus the integral and what we're going to call the arc.
You didn't take the picture? No?
Alright, so first do this and then do the arc. The top is the arc and then negative a to a. And that's gamma. So now what we're going to do is we're going to compute this guy and show he's independent of a, and show that as a goes to infinity, this goes to 0.
Okay, man. I need a picture with you.
I'm almost done. This is the last example.
I gotta go to class. I need like 3 people, right?
Yeah, 3 people. How do you volunteer?
I know. Group stuff. Okay. 1, 2, 3. Thank you guys.
Thanks. See ya. Okay, so look, so I'm decomposing gamma, which is that half semicircle thing, into negative a plus a to a along the real line, and then the arc, right? The whole thing is now, f of z is actually equal to g of z over this, where g of z is this guy, right? And g of z, so f of z, which is this, he has singularities at I and negative I. This is what's going to be the next thing. Obviously, too much to do in one class or one. But the singularities are here. He has singularities there. F has singularity there, and it has a singularity in minus I. But by picking the top semicircle, we're only encompassing this singularity, and so that we are not.
We're taking the image, right?
Huh?
The image.
We're taking the image of what?
Did you flip the arc?
No, we don't want to flip the arc. The thing is, so g of z, the whole point is now g of z. This g of z, which is this guy, g of z is this. G is going to be holomorphic on the upper half plane, on the z in the complex plane, such that the imaginary part of z is greater than or equal to 0. Meaning g, this function g, this guy right here, his only singularity is at negative I. And so that from the real line up, this g is holomorphic. It has no singularity. And we're going to use that. So actually first, let's just show that the integral around the arc. So first, the integral around the arc goes to 0. And how you do that? We're going to use that ML formula. We have that the integral along the arc, f of z dz, is less than or equal to a bound times the length. Well, what's the length of this thing? The length of a whole circle is 2 pi r. Right? Here the radius is a. So this is pi a. The length of this thing is pi a. And now we just need to maximize the function f along the arc. And I'm not going to do it, but it so happens that so we need to maximize this function along this arc. Well, actually, this is z squared minus negative 1 squared. So, no. This is this guy. And so this is 1 divided by these two things. Well, these two norms. The absolute value of this is the absolute value of this, is the absolute value of this, the absolute value of this times this. And now, these are the distances in the complex plane. So I'm saying, so how can I maximize, I'm talking about the distances from I and negative I to any point on this curve. If I want to maximize this function, I gotta minimize this down here. I gotta minimize the denominator, and I'm gonna maximize the function. So that I'm considering these lengths or whatever, for example, and I'm also considering these lengths. The smallest these lengths ever get, the smallest length, I guess, would be here. This is to this point at I, this is the smallest that length ever get. Any of these two lengths get. So that actually I can replace, this is less than or equal to, I can replace the minus I, this minus I to a plus I. No, this plus I to a minus I, because I'm taking this length from I, it's the smallest length. And we get that actually this f of z, I'm not going to do it, I can show you later, is bounded by 1 over the norm of a minus I to the fourth. Because we got a square here and a square there, so it becomes the fourth. And this goes to 0 as a goes to infinity. Right? Because I have a to the fourth, that's actually minus 1, I'm sorry. A is a positive real number, so that a minus 1 to the fourth has a power of a to the fourth, right? When I expand it. And at the top I only have 1 power of a. So now taking the limit as a goes to infinity, that goes to 0. So you see that the integral around the arc actually goes to 0 as a goes to infinity. And now we just so we have this guy. This is the guy we want. We gotta compute this guy. But by Cauchy integral, by the Cauchy guy, he tells us that the integral around any curve, for example, now we're gonna do of f of z dz, any closed curve that doesn't encompass any singularities. So by writing f of z as g of z over this, and only integrating on something that's in the upper half plane, the singularity of g of z is at negative I, so we're not touching it. Like, we're not even close to it. So that we were going to write this as g of z over z minus I squared dz. And now, this is nothing more than a coefficient in the power series expansion of g of z. Meaning, by the Cauchy integral formula, this is 2 pi I times, well, the power here is 2, and this is centered at I. This is, and it's supposed to be plus 1. It's k plus 1. Here, k plus 1. So actually, if this is 2, k is 1. This is g prime of I. Remember? Because g, alright, we have that g of anything. G of a is 1 over 2 pi I, integral around the curve, g of z over z minus a. Now, if I put a power here to the k plus 1, this becomes the k derivative times k factorial. Here, k is 1, because this is 2. So this is the first derivative. K factorial is 1. 1 factorial is 1. This is g prime of I. 2 pi I. Oh, this is what? What's g? G is, I got over there, so it's d over dz of 1 over z plus I squared, evaluated at z equals I. What's the derivative of this? This is negative 2 z plus I cubed, right? Evaluated at z equals I. It's 2 pi I. 2 pi I, plug in I get 2i. 2i cubed, so I get 2 pi I times negative 2 over negative 8i. Right? Because then 2i cubed is negative 8i. So now the negatives cancel. the 4 cancels with the a, I'm left, the I cancels with I, I'm left with pi over 2. So that the integral, so now we have this guy. This contour integral here is actually pi over 2. And now we just take a limit. And as you see, this calculation was independent of a. It was independent of the radius of the circle. At no point did a come into any of this calculation. So that we have that pi over 2 is, we can take the limit as a goes to infinity of this contour. This guy is equal to pi over 2 for any a. What I was saying is he was independent of a. Now, take the limit as a goes to infinity, but this guy, by that over there, is the limit of the product, the limit of the sum is the sum of limits, so this is limit as a goes to infinity, negative a to a, z, dz, plus limit as a goes to infinity of the integral around the arc. But we showed that as a goes to infinity, the integral around the arc is bounded. It actually goes to 0. So that this part goes to 0, and this part goes to negative infinity to infinity. And it actually, since A is along the real line, this is the copy of R in C. So this goes to 0, that part goes to that, and this is the integral from negative infinity to infinity of 1 over x squared plus 1 squared dx. This area down here is pi over 2. And we're done. Wow. Dude, it's too much, man. Okay, so, did anybody get anything out of this, bro? Please tell me.
I know where my course is going.
Yeah, so the idea was, your course you're gonna prove Moirer's theorem here. So Moirer's theorem, remember Moirer's theorem was the integral. If the integral around any closed curve is 0, then it's holomorphic. The hypothesis can be weakened to the integral around any triangle or any rectangle or any closed C1 curve. Well, piecewise C1 curve. So you can weaken it. So in your class, I don't know why he does the triangles. I like the circles so much better. They're so much easier. There's easy question on the parameterization of both. But whatever, it can be weakened to triangles or rectangles or anything. But it's enough to do it with circles. So yeah, so you're gonna do that. Eventually you're gonna do the integral theorem. You're gonna do all the stuff, a lot of the stuff that I did today. Just, I guess slowly and.
Yeah, because right now we're doing a whole lot of stuff. I'm like, why are we doing this thing with the triangles? So it's good to know where it's all headed.
But no, so the idea was, I lost the marker. So this actually, I proved the power series expansion over here. That finished the following or equivalent, the Open things. That finished the thing. We have that being holomorphic is the same thing as being complex differentiable, as having a power series expansion at every point, as the integral around any closed curve is 0, the partial with respect to z bar is 0. It's like I can give you a function who is, for example, take f of z equal to the norm of z squared or something. This is not a complex differentiable function because I can express it as this norm of z squared is actually z times z bar. You get me? You ever seen that?
Yeah.
And now, partial f partial z bar is equal to z, not equal to 0. You know, if I take the derivative with respect to z bar, the derivative of this guy is 1. This is just a coefficient, like a constant kind of, in terms of this variable. And so that it's z, it's not 0. So that this is not a holomorphic function. And so that's another. So this equal to 0 is another way to check if. Because eventually you'll see this. You'll see a lot of z times z bars.
Yeah.
And if you have a function that has z bars in it, automatically not complex differentiable. You take the derivative with respect to z bar, and you're gonna get something that's non-zero. It's gotta be a pure power series of z. There can't be no z bars anywhere. That's one way to look at them.
What was the notation you're using for the boundary? It looked like a Cyrillic D, just like in the partial derivative notation.
Yeah, there's a partial sign
Why is it? Is there a reason why it uses the same letter? Is it related to partial derivatives in some way?
No.
No.
It's just notation. It's how I learned it is just for any domain D, you have the boundary. Because in homology, this is called the boundary operator.
Okay.
In homology, you know what we're doing right now. You have boundary of k plus 1 to the boundary of k. You have the boundary in algebraic topology. You have all these complexes, and you have this boundary operator and the boundary just literally means the boundary.
Right.
So that whenever you have a domain, this is the boundary of the domain, and it's just a curve that encloses the domain. It's like complex variables is really nice. It's really useful. As you see, I can compute this guy. Over the real numbers, you can never compute this guy. Ever. He has no antiderivative. And in terms of elementary functions, you can't compute this guy. But you could using Cauchy integral formula, but it's letting that circle, the radius of that circle go to infinity. You end up just integrating along the real line.
Sweet.
Oh,
Just
call it that. I think it looks like this.
Yeah, it's weird. I mean, so far we hardly